Hello, Algebra 2AB. Today we're starting a new chapter, Chapter 12, which deals with triangles. So where we're going to start in day one is talking about Pythagorean theorem and its converse. All right, your homework assignment is going to be Chapter 12, Day 1 worksheet. It's going to be rather short. The notes are going to be rather abbreviated as well because obviously all these concepts you've talked about in previous classes. All right, so today we're talking about Pythagorean theorem. Now, one thing that we need to know before we can use Pythagorean theorem is what's the hypotenuse and what are the legs. Okay, so the hypotenuse is the side that's opposite of that right angle. Oops, got to bring up my tools. Let's go with the regular pen. There we go. All right, so the side opposite of the right angle is the hypotenuse, whereas the other two sides are the legs. Those are the sides that are adjacent to the right angle. Okay, so the hypotenuse in a right triangle is always going to be that side that's opposite that right angle. Now, getting on to the theorem, right, it states in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs, which just means c squared equals a squared plus b squared. Okay, a lot of people know Pythagorean theorem is a squared plus b squared equals c squared. It's the same thing. I just want to write it as c squared equals a squared plus b squared so that we don't get confused when we move on to the converse. It's going to be a little bit easier to approach the converse with the equation written like this. Okay, so let's get on to our first example. So in example 1, we have one missing side length in this right triangle. Whenever we have two sides out of 3 in a right triangle, we can use Pythagorean theorem to find that missing side. All right, so the first thing that we'd want to do, though, is mark the hypotenuse. All right, no matter if we have it or if we don't, I like marking that hypotenuse first because then we're not going to confuse a leg with the hypotenuse. All right, so the side opposite that right angle is the hypotenuse, so I'm going to mark that as C. And then for the other two, we've got A and B. And it doesn't matter what you call A and what you call B, so you just mark them. All right, so A is 8. B is 6. You could write B as 8 and A as 6. It doesn't matter. All right, and now for the first few examples, I'm just going to write down the Pythagorean theorem. So c squared equals a squared plus b squared. And then substitute what I know each one of those side lengths to be. So c squared, that's just going to be x squared. Instead of a, we're going to put 8. So that's 8 squared. Instead of b, 6. So we have 6 squared. Now we can find those values. 8 squared is just 64. 6 squared is 36. If we find the sum, we'd get 100. And now we just need to get rid of this square. We need to figure out what x is, okay, because that's what we're looking for. All right, so to get rid of that square, we're going to take the square root. Now, algebraically speaking here on this step, when we take the square root of 100, we could get positive and negative 10. Both of those would satisfy that original equation, x squared equals 100. But only one of them makes sense in the context of the problem here. All right, this side length cannot be negative 10. All right, there's no way. That distance isn't going to be negative 10. No matter what direction we're talking about, if it was north, south, east, west, we're still 10 units away. Okay, so the only solution that makes sense in this case is positive 10. All right, in example 2, we need to mark our hypotenuse. So opposite that right angle is C. And the other ones we can call A and B. Okay, that's a weird B. There we go, that's a little bit better. All right, so now we've got C squared equals A squared plus B squared. Plug in what we know. C is 14.9. A is 12. We don't know what B is. We're just going to write X. Now we're going to square each one of these values. Okay, so let's bring out our calculator here if necessary. All right, 14.9 squared is what's up first. So we get 222.01. 12 squared, we should know that one. That's 144. All right, if we subtract 144 on both sides so that we can get x squared by itself, we get 78.01. Now let's take the square root. All right, we want to take the square root to get x by itself. Now once again, like we said, algebraically speaking, we'd get two solutions, one positive and one negative. But in the context of the problem, that distance is not going to be negative. All right, so we've got 8.83. All right. I know in the directions up here for example 1, it says round your answers to the nearest tenth if necessary. We didn't need to. And then if the directions don't say anything, I usually like rounding to the nearest hundredth. All right, moving on here. Now, these problems are the same types of problems, just the focus here is on the simplest radical form. So we need to review how we simplify radicals. Okay, so we're going to start this like any other problem. All right, mark the hypotenuse first, then the legs. Write out the formula. Substitute what we know. So instead of c, I'm going to write x. Instead of a, I'm going to write 5. And then instead of b, we're going to write 5 root 2. Now one thing that we have to be really careful about here is in the formula, it says we're squaring whatever b is. This says b squared. So whatever b is, we need to square that value. Now b could be one long, complex formula or expression. All right, if that was the case, we need to square that whole thing no matter what it is. In this case, b is 5 times the square root of 2. So we need to square that whole thing. So you're going to see me write down parentheses, and that's why we need to square both of these parts. All right, if we just type it into our calculator as 5 root 2 squared, all right, it's not going to do the right thing. It's just going to square that value. It's not going to square that. So it's not really squaring all of what b is. All right, so we've got 5 squared, which is 25. And like so, since we're going to square both of these values, 5 squared is 25, and then root 2 squared, the square root and the square just undoes each other, so we just have 2. So that's 25 times 2, which of course is 50. Okay, 25 plus 50 is 75. And now, of course, we take the square root. It's just going to be the positive one. That would be the solution. But then it says leave your answer in simplest radical form. The square root of 75 is not in simplest radical form. What we've got to do is we've got to take out all of those perfect square factors of 75. Now, what we've used in the past in previous chapters was a factor tree. Okay, probably one of the most common methods. There's two different methods that we could go about using that factor tree, and I'm just going to talk about this in a little bit more detail in this example. We could go with taking out the lowest primes, and there's a lot of people that just like taking out those lowest primes, or we could also take out the biggest perfect square. Okay, taking out those lowest primes would be like taking out factors of 2 and 3 and so on, those lowest prime numbers. Now taking out the biggest perfect square might be a little bit more difficult initially, but it's easier in the end result. We got to figure out what is the biggest perfect square factor of 75. And in this case, that would be 25. 25 times what is 75? Well, that's 3. So what we're really saying when we're doing this factor tree here is root 25 times root 3 is root 75. And now we can just simplify this. The square root of 25 is 5. So this is really 5 times the square root of 3. Like I said, we want a little bit more detail on that one, just because, maybe it's been a while since we've simplified radicals. All right, now in example 4, we know the hypotenuse. We don't know one of the legs. So once again, let's mark them. So we have c squared equals a squared plus b squared. Substitute the values that we know. Now, b is the square root of 170. And when we square that value, that square root and that square just undoes each other, and we just get 170. All right, 14 squared is 196. So we get 196 equals x squared plus 170. Now we got to solve for x squared, so subtract 170, and we get 26. Take the square root. We get the square root of 26. And the next thing that we should do is try to see if we can simplify this any further. All right, it's going to be able to be simplified as long as there's a perfect square factor that isn't 1. Okay, so we're going to go about using the lowest primes method now. So first, we take a look at the lowest prime, 2, and is it a factor of 26? That'd be a yes, because 2 times 13 is 26. All right, and then we would once again try to do this here as well. So for 13, is there a lowest possible prime that we could take out? Can't take out 2, 3, 5, 7, 11, and obviously that's 13, so that's it. All right, so that means the square root of 26 is in simplest radical form already. All right, now finally for the last example. This last example is going to go over the converse, and there's actually 4 parts to this last example. And the converse can really be used to determine whether this triangle is right, acute, or obtuse. All right, so the converse of Pythagorean theorem just reads, if the triangle is right, then c squared equals a squared plus b squared works. Okay, the Pythagorean theorem was, if it's a right triangle, then c squared equals a squared plus b squared. So we're just flipping that around. All right, but let's say it doesn't equal a squared plus b squared. We could still use that to determine whether it's acute or whether it's right. And the reason why we set it up as c squared equals a squared plus b squared is because then this is going to make a little bit more sense. So it says if c squared is less than a squared plus b squared, then the triangle is acute. Okay, so that means if the hypotenuse squared is less than the sum of these, the sum of the squares of the legs, then it's acute. So that means if we set it up like this, less than corresponds to acute. Right? If c squared is greater than a squared plus b squared, then the triangle is obtuse. So that means greater than is going to correspond to obtuse. This only works if we set up the Pythagorean theorem this way. Okay, and obviously we can do it if we write a squared plus b squared equals c squared, just then these aren't going to correspond to acute and obtuse. All right, so we can just think about it. If c squared is less than, then that triangle is acute. C squared is greater than, then it's obtuse. Okay, and hopefully that makes some sense. All right, if we take a look at example 5, notice we have no picture, but we don't need a picture. Right? Although we're not going to know what side length corresponds to what, it doesn't really matter. Like those 2 legs are interchangeable. Okay, the only thing that matters is, can we identify the hypotenuse? And the hypotenuse should be the biggest side, or sorry, the longest side. So that means 15 is going to be C, and A and B is 9 and 12. All right, so using C squared and a squared plus b squared, we can determine whether this thing is right, acute, or obtuse. I'm just going to leave a little blank there because we don't really know whether it's equal, less than, or greater than at the beginning. All right, so I'm just going to leave that blank there until we figure it out. All right, so that means we'd have 15 squared and 9 squared plus 12 squared. Now, these problems are actually pretty darn simple. All we got to do is type the stuff into our calculator if we don't know it. All right, so 15 squared is just 225. 9 squared plus 12 squared, well, that's 81 plus 144. That's 225. All right, so in this case, we have 225 equals 225. All right, so that means that this is a right triangle because c squared equals a squared plus b squared. Whoops. Okay. Oops, I don't know what I did there. There we go, get my pen back. Okay, so like we said, c squared equals a squared plus b squared, so this thing is right. Right now, in part B, we identified the longest side, that's the 13 meters. The other two is our A and B. So we have 13 squared on one side, and then 10.6 squared plus 11.2 squared on the other side. 13 squared, that's an easy one, that's 169. All right, the 10.6 squared plus 11.2 squared, we might need to type that into our calculator. The cool thing about this is we can type this whole thing. Just type it in exactly as shown, right into the calculator. You're going to get the right value because what we wrote down and what we type into the calculator, you know, is going to be the same in terms of the order of operations. All right, so 169 is less than 237.6, or sorry, 0.8. So since it's less than, it's acute. All right, for C, all right, 15.3 is our hypotenuse. The other two are the legs. So when we type this out, we get a bunch of decimals here. And that's all good because we can just type it into our calculator anyway. Or if we had to by hand, we could just write it out, figure it out. So 15.3 squared is 234.09. 10.9 squared plus 13.5 squared is 301.06. Right, and we get c squared is less than a squared plus b squared again. So that's also acute. Guessing you can figure out what this one's going to be. All right, but let's go ahead. 14.6 is going to be c, our hypotenuse. So we have 14.6 squared, 9.6 squared plus 7 squared. 14.6 squared is 213.16. 9.6 squared plus 7 squared is 141.16. So in this example, c squared is greater than a squared plus b squared, and that corresponds to an obtuse triangle. All right, folks, that's it. That's Pythagorean theorem and converse of Pythagorean theorem. All right, so I'll be posting the homework as well as the answers. If you have any questions, make sure to send me an email. All right, thank you and have a good day.